Good morning, and thanks for coming to my talk. Again, I'm Brandon Baker, lead security engineer for Windows virtualization, and I get to work on the Microsoft Windows hypervisor. So about 5 years ago, I interviewed at Microsoft, and I interviewed with a couple different groups. One of the groups I interviewed with talking about things about ring -1 and new instructions to the x86 instruction set. And I knew I was hooked at that point. So that's what this talk's going to be about. Virtualization is some pretty exciting stuff. It's really useful for getting work done. And we're building virtualization into Windows and Windows Server. So the talk today is going to be on a couple points. The first one is, why are we building a hypervisor, or why are we building a hypervisor into Windows? What's so cool about hypervisors? The next thing is going to be kind of a quick background and some architecture on Windows Server virtualization and the hypervisor. I could spend hours just talking about the architecture of the hypervisor. We don't have time for that today. But if you look on the conference CD, the slide deck that's on there has a lot more information on the architecture of the hypervisor and Windows Server virtualization. And then the bulk of the talk, I'm going to be talking about the security characteristics of what we're building. And a lot of this is going to be generalized to virtualization, applying across the board. And other things are going to be very specific to the technology that we're building. By and large, we're seeing more and more virtualization all the time. Like I said before, it's just a really useful way to get work done. But as security professionals, we have to think about, as we're securing systems or looking at ways to find vulnerabilities in systems, what's the impact on virtualization on the security community? The next area is going to be around deployment considerations. If you're thinking about using virtualization or you're looking at this technology, what are some best practices for implementing and deploying virtualization? What are the security concerns that virtualization brings with it? Solves a lot of business problems. That's great. Solves some technical and security issues. That's great. But in and of itself, it also has its own security issues that are really important to keep in mind. And then finally, going to have a few things to say on some future directions in virtualization and just some general topics around the industry on where virtualization is heading. I'd like to ask, if you can, maybe hold the questions to the end. I'm going to try to leave some time to go through and take questions at the end. I really like to talk to people one-on-one or a few people around a whiteboard too. So if you see me through the rest of the conference and want to talk in more detail, grab me. I'll try to go over to the Microsoft booth. I assume there's a Microsoft booth. I've not ever been to it before. This afternoon. So if you want to stop by and talk more, that's great too. All right, so why a hypervisor? Why am I so excited about a hypervisor? Why do I think they're so kick-ass? I mean, the first point is we're talking about something that's a thin, low-level microkernel, right? It runs below the operating system, right in between that interface at the hardware OS interface. And, us OS and kernel geeks, the lower you get, closer you get to hardware, the cooler things get. But more importantly, it addresses an issue with virtualization and software virtualization today. In order to make things like virtual PC and virtual server and maybe VMware Workstation, these software virtualization techniques effective and work correctly, we have to do kind of a mechanism we call ring compression. Well, in moving over to hardware virtualization in a hypervisor, we eliminate that point of complexity. And this also means that with hardware virtualization in a hypervisor, we can run an operating system without any modification at all. In order to make ring compression work correctly, we have to kind of modify or change up some bytes in the operating system on the fly so it doesn't know it's being compressed, doesn't know it's being virtualized in the way that it is. With the hardware virtualization in a hypervisor, we get to run an OS essentially raw, bare inside the metal, inside of a partition. And as we're running everything as partitions, we get some additional defense in depth, and we'll talk about that some more later on. And by and large, we think that this model, this architecture of a hypervisor is the best way to use the hardware that Intel and AMD are putting out today and leverage the future hardware investments, some of which we'll talk about at the end as well. And finally, I think this is really kind of the right way to address scalability. In the future, as we're looking at systems running large numbers of virtual machines on systems with large number of CPUs, we think a hypervisor approach is really the right way to address scalability. So what is the hypervisor and what's the system it's a part of? This has been a project at Microsoft codenamed Viridian. And we're really talking about full fidelity machine virtualization. Right? This isn't like software virtualization. This isn't like, say, maybe like the Common Language Runtime or the Java VM, which is an abstract virtual machine. We're talking about creating a virtual machine that's the full x86 PC. This is something that we're building into Windows. This will be a component of Windows Server 2008. The Windows Server virtualization component will be available within 180 days of Server 08 RTM. It's kind of the realities of dealing with an evolving hardware platform and also an evolving OS platform. And finally, Windows Server virtualization installs as a role in Server Core. Server Core is some new technology that's built into Windows Server 2008 that lets you install basically just the bare minimum of the OS. Very little more than is necessary to do a role, in our case, virtualization. Ian McDonald is giving a talk on this tomorrow, so if you're interested in this technology more, you can go to that. All right. So the system is comprised of three major components. The first one's a hypervisor, but it's not the only thing. We also have a virtualization stack, and we have a collection of virtual devices. As the system is hypervisor-based, we take advantage of and we also require the hardware virtualization extensions that are present in Intel VT and AMD SVM hardware. Basically, most of the newer processors that have been available for the last 9-12 months. We are supporting x64, 64-bit hardware only. This is a server product, server market. Having a 32-bit hypervisor really would constrain us on the guests we can run. So what we're saying here is this does require 64-bit hardware, and then the operating systems that we can run on top of it, anything. 64-bit, 32-bit, 16-bit if you want to run DOS still on a really big piece of hardware. So kind of give some of the history of the background here on kind of the old way of, I mentioned ring compression before and what that was. So software virtualization systems like Virtual Server, running an operating system, essentially the host OS. We've got ring 0 for the kernel, ring 3 for the applications that are running. And when you want to activate virtualization, you need some sort of virtual machine monitor. And under software virtualization systems, these typically run essentially alongside with or cooperatively with that kernel, inside the same address space. And then when you want to run a guest operating system, it runs it essentially as an application, basically. You can almost think of it like that. And it puts that guest OS kernel into ring 1. Right? And then the guest applications themselves can still run as ring 3 sort of native applications. But in order to make that operating system work correctly, we have to make it believe that it's running in ring 0. So any instructions that it does that try to determine or would be able to see that, we have to intercept and do runtime translation, binary translation, on that operating system, essentially modifying its code bytes so that it sees ring 0, even though it's running in ring 1. And that's a complexity point. From a security standpoint, complexity is often the enemy of security. While that works, it works great. It's something that is a challenge and something that would be nice to kind of get rid of. So now let's talk about Windows Server virtualization, hardware virtualization, a hypervisor. Right? I'm going to step this through to introduce the components and also essentially talk about them in boot order on Server 2008. So kind of at the beginning of time, we have the kernel. The kernel is just booted on this server hardware. Pretty early on, the kernel loads device drivers. And what we're saying now is that one of those device drivers is the hypervisor. Right? So really early on, the OS launches the hypervisor essentially underneath itself. This now puts that root operating system into a partition. Right? So it's kind of hoisted itself up, launched the hypervisor underneath. And we're able to do this because of hardware virtualization. Now the rest of the operating system comes online. If this is Server Core, it's really just a foundation of Windows and very little more than what's necessary to run virtualization. In this case, we have these collection of virtual devices. The virtual devices interface with the real device drivers on the system to provide direct or indirect emulated device access for guest operating systems. And then we have some user mode components. And this is that virtualization stack, sort of that third piece of Windows Server virtualization. The virtualization stack has a management service that provides and exposes a WMI interface. The WMI interface allows you to do things like manage, start, stop, launch VMs remotely. Microsoft System Center will be supporting this so you can deploy and manage really large, complex sets of servers with lots of virtual machines. And if you can imagine, if you have a data center of 1,000 physical machines, each running dozens of virtual machines, the management space on that explodes pretty quickly. And then now when we want to run a guest, a virtual machine, we launch what we call a worker process. Right? This is a user mode process that contains a virtual or an emulated motherboard and a collection of emulated devices for a guest. So now we'll bring the guest into existence, and it runs as a separate partition. But the interesting thing here is the guest kernel, the guest OS, also runs in ring 0. You know, when I mentioned ring -1, a hypervisor down in monitor mode, while it's convenient and kind of interesting to think of it that way, actually everything here is actually now a partition. The root, the OS that was there initially is in a partition. Each of the guests is a partition. The hypervisor itself is really effectively just another partition. It just happens to be a specially privileged one, a monitor mode partition. And there are control structures. On Intel, they're called the VMCS. On AMD, it's the VMCB. It's a VM control structure that says what things that partition is able to do. What hardware can it touch? What instructions can it execute? For our hypervisor, we do expose it up to a guest. So we have a well-defined interface that a guest operating system can query to say, well, what am I running on a hypervisor? Which version? Whose is it? The reason we do that is, while we can run an operating system native without modification, that's great. But there's certainly cases where it makes sense for that operating system to know that it's running in a virtual environment so it can do things a little bit more optimally. So we call these guest OS enlightenments. One of the things and another component of Viridian here is something we call VM bus. It's a virtual machine bus. This provides an optimized or direct path from a guest OS into that root partition. Okay. And another thing the guest OS can load are virtual service clients, VSCs. And a VSC has a direct way to talk to a corresponding VSP, like for storage or for network, across VM bus. And VM bus, again, it's a shared memory transport so that you have certain physical pages which are mapped to both the guest and the root. We have one set of VM bus per guest, so the guests don't share VM bus connections. There's a one-to-one from the parent to each child operating system, root to guest. And through this mechanism, we don't have to essentially interrupt or intercept into the hypervisor every time a guest OS tries to do some device access. An example of this might be trying to do a write out to an IDE controller. If an operating system is not enlightened, it's going to try to do a lot of I/O instructions, ins and outs, to queue up some data, spin up the disk, write the disk out. Each one of those I/O operations is going to generate an intercept. An intercept is a new hardware concept that the virtual machine hardware generates when a guest OS essentially does something that its VMCS or VMCB says that it's not directly allowed to do on hardware. So for us, these guests can't touch real hardware. So if they try to do a virtual I/O, it's intercepted, comes down to the hypervisor, goes over, and goes up to that root partition. That takes time. A lot of instruction cycles involved there for that round trip. And one I/O operation might take 5 or 6 round trips. What we can do across VM bus is actually have a direct transport for that, say for instance, that storage request to be intercepted in the storage stack in that guest OS, written to that shared memory, and then piped directly over to the root partition. where it can be written out to disk. And then for each subsequent guest partition that's launched, up in the top left there, we launch another worker process. One worker process per guest. One instance of VMBus per guest. So when we're thinking about and talking about virtualization security and virtualization attacks, the things that we're concerned, that I'm thinking about, are related to somebody coming in, a malicious hacker, script kiddie of the world, coming through and compromising some application that's running inside of a guest partition. It's kind of the toehold point, right? These guests are where you're going to run your internet-facing applications and internet services, so these are the things that are going to be exposed to the most risk. That root partition can be locked down, tucked away. We'll talk a little bit more about that. But the guests are where you're going to have your greatest exposure. So if a guest application were to be compromised, let's say it's running with privilege, or you have a kernel bug in the OS that you're running here. Right? Worst case scenario, that guest kernel has now been owned. So what we have to be concerned about is accepting this as a reality for what could happen inside of a virtual machine. We have to ensure that if that were to occur, that guest can't break out of the confines of its partition. It can't affect another guest. We don't want it to compromise the hypervisor. We're also concerned about it compromising the root partition. If a guest were to compromise the root partition, it could get access to all of the other guests on the machine. Right. So let's spend a little time talking in some more detail about the hypervisor itself and what it is. It really is a partitioning kernel. Our hypervisor is fairly thin. We've pushed up a lot of the classic virtualization functions up into the virtualization stack. Really what it's doing is it's managing the base resources on the machine, creating these partitions. It really only deals with memory and CPU and generating these intercepts. The rest of the emulation for most devices lie inside the virtualization stack. And this makes it really thin, really small. Right? And this is a really base component. We have to be concerned about reliability here. And also as such, we also don't have device drivers inside of our hypervisor. Right? We're utilizing the device driver model inside of Windows. This way we don't have to have device drivers be completely rewritten for a new environment. We can take advantage of the servicing and updating and everything else that you get inside of Windows, and can keep the hypervisor a static monolithic image that doesn't change. Well, except for updates for itself, of course. We also have a really well-defined interface from the hypervisor up into each of those partitions. As I mentioned before, our hypervisor will announce its presence. A guest can go through a series of protocols of querying a CPU ID leaf, and essentially the hypervisor will respond back with, hello, this is the Microsoft Hypervisor version 1.0. And we do that to allow people to create these enlightenments, to do more optimal instructions, more optimal ways of flushing memory and other things like that inside of a guest OS. Essentially, our take here is we don't hide virtualization because we need these operating systems to run as good as they can. I think I've talked about most of the things for the virtualization stack, those pieces inside the root OS. And the key thing here is this is really where the bulk of virtualization and emulation actually happens. Okay? All right. So now we can really kind of auger in and just kind of go into the security characteristics of this system. I want to talk about some of the things that we're doing and some of the things that we're not doing to be pretty clear about what the security goals and non-goals of the system are. Right. So I've got up here the list of security assumptions that we kind of go off of. The first and most important one is we always treat those guest virtual machines as untrusted. The assumption always has to be that they've potentially been compromised. So we can't rely on any correct behavior in a guest OS, even on the enlightenments, even on virtual service clients. The expectation is they're going to try to do bad things to the hypervisor and the root partition. Right? That said, we do recognize that the root partition needs to be trusted by the hypervisor, and the root partition, essentially as a role of a parent, needs to be trusted by all the guest OSs that it's creating, its children. The third thing here is we also have an assumption that the guests are going to try to run in every processor mode available and switch between them and essentially just try to, essentially the sky's the limit inside of a guest because we're allowing them to run on real hardware and really run in ring 0 or really run in 16-bit, 32-bit, 64-bit, long mode, real mode, everything else, right? The expectation is we have to be able to handle every possible transition there. Another one of our assumptions is that the hypercall interface itself is going to be well known, well understood, and potentially going to be attempted by a hostile, malicious, compromised guest. Right? We don't get to hide the fact that there is that interface there. So the expectation is the guest will try every possible interface that's open and available to it. I mentioned how we'll even let you know what version of the Windows hypervisor that's there. And the final point is something important to kind of make developers understand and always aware of is that the security community and hackers at large are going to understand this system. Right? They're going to reverse engineer the hypervisor. Right? IDA Pro is a really powerful tool. The hypervisor is really small. Its internal design is going to be understood. So we have to understand that there can't be any security through obscurity in the functionality of the hypervisor. Although that said, IDA Pro right now doesn't have the Intel VT and AMD SVM instructions in it yet. So if you try to disassemble the hypervisor, it doesn't quite work yet. So if anybody knows ILFAC or the guys at Data Rescue, a couple of us around here would really like that fixed. All right. So now we come down to, kind of what are the security goals for the system? What are we saying that, it's most important that we do here? It really comes down to isolation. Right? Isolation of those guest partitions is what we're signing up to do and what we have to protect. We need to protect the confidentiality and the integrity of data inside of a guest from all the other guests on the machine. Right? Otherwise, virtualization here just won't be useful. And in order to achieve this, we have some internal design goals around separation, right? Making sure that we have a unique worker process per guest, that we have a unique instance of VM bus per guest, and that we also protect or provide non-interference so that one guest can't see the contents of another guest or modify its contents. And this is a pretty strong stance, and any instance where we find a bug or an issue with the software that could allow one of these to be violated, it's priority one, we have to fix it. The flip side, and really equally as important, is to really be clear about the things that we're not doing with the hypervisor and with Windows Server virtualization. We're running on shared hardware, and there is always the threat of a potential for essentially what I call hardware bleed-through or inference attacks. And this is to say not that one guest can find some issue with the hardware and see another guest's contents. This is really just more around the issue of a guest operating system, because it's on shared hardware, has the potential to see when another guest is present, or that there are even other guests on the system, and maybe when they're doing something. You can kind of think of it maybe like your hotel room here. You really can't hear the people talking and what they're saying in the room next to you, but you can probably hear when they're coming in and out of their room, or maybe when they're using their shower, maybe your water pressure drops. That's the reality of any virtualization system on shared hardware. And that also means that there's a potential threat or risk for covert channels. Right? Two compromised guests, not allowed to talk to each other, but they can potentially manipulate or modulate those things to signal to each other. By and large, security community, this really isn't that big of a concern. This is really kind of an issue sort of for kind of military level, high level specification, uber security systems. But it's important to recognize where the limitations are on virtualization and really what the impact is for deploying and using virtualization. Another issue with essentially shared hardware and shared services is there's the potential or risk for availability attacks. It's something that we can't guarantee to the same degree that we can guarantee confidentiality and integrity protection. Right? There's always the risk that a guest operating system, if compromised, could simply just flood the system. Right? There are a lot of things we can do to block that and prevent that, but you can only go so far because there might be legitimate times when a guest OS really is the only one processing and really does need to actually do a lot of network or storage access. And again, this is another reality of virtualization. It's not necessarily specific to our system. It's broadly across all virtualization. Right. We're not protecting guests from their root partition. And the root partition essentially has all the internal state for that guest. And that's just something we have to accept. If the root partition is compromised, the guests are compromised. And likewise, as I showed sort of in that stepwise diagram, the root partition is there, at least some small part of it, before the hypervisor gets launched. And while the root partition runs in a separate partition, doesn't have direct memory access, modifying page tables to get memory mappings on the hypervisor, they have separate address spaces, the hypervisor could still tamper with, the root partition could still tamper with the hypervisor as it's launching it. And because the root partition has access to physical devices still, right? So the actual storage controller, network controller, there's always the risk for what we call a DMA attack, right? Programming that physical device to bypass those memory protections and just raw read or write into the hypervisor's memory. Now, both of those concerns are things that future hardware is going to be looking to address. But as it stands today, that's just simply something we have to recognize. And finally, things that we're not doing in this version of Windows Server Virtualization is we're not taking advantage of, in the hypervisor itself, things like trusted hardware. So the hypervisor is not using a TPM. Hypervisor is not utilizing any device assignment capabilities. These are future investments we're looking at using. Of course, that said, if that root partition were to be using a TPM, for instance, we wouldn't interfere with that. It's another device. The root partition gets to use physical devices. That's great. All right, so what are some of the investments that we've put into making that hypervisor really tough to help ensure we have some, achieve those isolation goals? And the first one, it's pretty interesting and important one, is that we have a separate address space for the hypervisor from the root partition. And this is different than the software VMMs, where the virtual machine monitor ran inside the kernel. Right now we're talking the virtual machine monitor, the hypervisor runs in a completely separate address space, even than that root partition, and the guests. If we were to have a flaw in the hypervisor that allowed a guest to, say, for instance, reference some memory, the memory the guest is referencing, the addresses the guest could reference there, don't mean anything, don't translate to addresses inside the hypervisor. It's kind of different than if you think about maybe a user mode to kernel mode exploit or issue today, where a user mode process could potentially reference an address in the kernel or get the kernel to reference a user mode address, leading to some vulnerability. We don't have that issue here because we are in separate address spaces. Right. Don't have third-party code in the hypervisor. It's just the code that we've built. It's small. It's one binary. Doesn't change. We're limiting the number of channels from a guest into the hypervisor. And we have that well-defined hypervisor hypercall interface. It's not multiplexed. Really, we kind of want essentially a one interface to one code path separation for the hypercalls, not something complex or multiplexed like an ioctl interface to where one ioctl could represent 50 different functions. We don't allow guest-to-guest communication. And what I mean by that is a guest can't use some virtualization function or backdoor or hypervisor interface to send data to another guest. If a guest wants to talk to a guest, it has to go out through the network interface. We also don't allow shared memory between guests. Right? So for instance, VMBus, where we do have shared memory, is just between a guest and the root. These are separate. We want to reduce and eliminate any potential for guest-to-guest collapse and isolation. And we block guests from touching real hardware I/O. If a guest wants to do something to a network or serial port or anything else like that, it's going to get intercepted. It's going to get passed into the hypervisor and up to the the root partition. Right? So the notion of a DMA attack from a guest is mitigated through this approach. So I'm a pretty big fan of mitigation technologies. I recognize that software always has the potential for bugs and for vulnerabilities, and it's really important to put some things in place that, even given a bug, can you make it more difficult for somebody to actually compromise that bug and turn it into an exploit? And so we've built the hypervisor with a whole host of these technologies. The first one, we're using /GS, stack cookies. This means if we happen to have an unchecked stack overflow inside the hypervisor, the attacker can't overwrite the return address. Right? That's one potential attack that's been mitigated, at least through that specific path. In addition, we are using hardware no execute. And this means that all of the hypervisor's data pages are marked non-executable. So again, if there happened to be some unchecked overwrite somewhere that allowed a guest to put its, specify some data, some instructions to go inside a hypervisor memory, it can't use that to now actually gain execution inside that space. The hypervisor's code pages are marked read-only in hardware. And again, so if there's an unchecked write someplace that would try to modify some hypervisor code pages, the hardware is going to stop that. Again, trying to shut down these avenues of, given the potential, say that there is a bug someplace, that bug can't be leveraged to actually now gain execution and compromise the hypervisor. Each of these things by themselves isn't super effective, and the combination of them is actually far more interesting. Right. We also have memory guard pages to detect the condition of a stack overflow or stack overrun or stack underrun. We don't have a really complex exception handling model inside the hypervisor. By and large, actually, there really is no exception handling. If we detect a violation, say, for instance, of the stack cookie got overwritten, the response here at this point is we have to assume that something's gone very bad and that it's time to actually go ahead and just take the machine down gracefully. So this is where a bug check would actually happen. So basically, if we detect the potential for a vulnerability or compromise, the response is bug check the machine and get that data actually logged out. It's a very similar mechanism to what the Windows kernel itself does in a very, essentially far removed, compromised detected situation. It's really not worth advancing. This also means that a lot of the exploits against exception handlers that exist in more complex code, with structured exception handling, just aren't present inside the hypervisor. And finally, the hypervisor's binary image on disk inside the root partition is signed, and it's checked with code integrity and driver signing. We're spending a lot of time, we're putting the hypervisor and the root components through the Microsoft Security Development Lifecycle, the SDL. And this means that we're spending a lot of time doing threat modeling. We're performing static analysis across the hypervisor and the other virtualization stack components to try to find vulnerabilities and flaws. We're performing our own fuzz testing and penetration testing in-house. We've got a dedicated team of test developers who essentially work alongside with the developers and implement tests, including security tests and penetration tests, to try to find as many of these vulnerabilities and issues as we can before the product ships. I mean, essentially, what we're trying to find are ways in which that component there in the sort of the top right, that compromised guest, could potentially try to break out and fix those bugs before we ship. It's a pretty dense slide. This is sort of highlighting the security model that the hypervisor exposes to the root partition. Right? The hypervisor really is only managing a couple resources: memory, CPU, and access to I/O. And as such, the root partition can tell the hypervisor, okay, well, who gets to own what memory? Who gets what CPU when? Who can access which I/O devices? And the hypervisor will enforce those policies. So we can do some things that are kind of interesting. For instance, if a guest has been given some memory and the guest has read-write access to that memory, the hypervisor actually could, under the covers, set that memory to actually only be read-only, or maybe not even have any access rights. So that every time a guest tries to access that memory, generates an intercept, we pass the intercept to the root partition. It's really useful for virtualizing devices and device I/O ranges, but there's some other interesting things that could be leveraged there in the future. We rely on the fact that the hardware guarantees the processor state won't bleed through as in like readable and writable between guests. So if we give a processor to one guest, take it away at some point, we give it to another guest, hardware will guarantee that cache registers will be isolated, will be flushed and replaced with the contents for the other guests, so you can't see or modify the previous guest's contents. And that the TLB will be flushed as appropriate where necessary, so that the second guest can't inadvertently map addresses and access memory for the first guest. And that I/O policy says that the hypervisor will enforce whatever I/O policy the root partition says. Some I/O accesses maybe just get dropped on the floor. Essentially, a write to an I/O port might just result in nothing happening, and a read might just always return a page full of Fs or something. And other I/O accesses, the root partition wants to take those intercepts and emulate some device behavior. And finally, the hypercall interface, right? The interface that a guest operating system can call into to sort of become hypervisor aware and do things a little bit more efficiently. There's a collection of interfaces that are essentially exposed to all guests, but only certain guests have privileges to call those hypercalls. So for instance, the root partition is the only partition that can call the create partition hypercall. We don't want a guest OS to be able to create another guest underneath it. We're not supporting any sort of form of nested virtualization here in Windows Server virtualization, at least not in this version. So managing virtual machines and saying who can create them and start and stop them often falls in through departmental roles. Right? So you might want to have a finance department be able to create some virtual machines, and an engineering department manage and create another set of virtual machines, but not allow them to actually manage or manipulate each other's virtual machines. So in order to implement this, we're using something called Authorization Manager, AZMan. AZMan was introduced in Server 2003. It lets you just have fine-grained, role-based access control to say what groups of people can do things in certain operations. And so for us, it's things like starting, stopping, configuring a VM, saying what virtual machine has access to what virtual devices. And what that allows us to do is give somebody the ability to be an administrator for a collection of virtual machines without actually having to be physical local administrator on the server itself. Let's skip ahead and talk a little bit about time virtualization. I wanted to put this in here just to sort of give some insight into some of the design decisions or trade-offs that we make pretty regularly on building the hypervisor. Time's a really interesting one because virtual machines are really affected in really unique ways by time, in a way that a physical machine, an OS running on a separate piece of physical hardware, would never really see. And so we recognize that there's really kind of three categories of time. The first major one is calendar time, stuff that you see off a clock. Right? Virtual machines get access to calendar time through an emulated device, an emulated real-time clock. But then there's actually sort of lower level, like machine time. Right? Things like, how many processor cycles have actually clicked by since I've last executed. And we provide to virtual machines a virtual APIC. This is a aperiodic programmable interface timer that a guest can program to get interrupts sent to it. We also provide a synthetic interrupt controller that provides a little bit more robust interrupts that a guest can program to get certain time events to come back to it. Right? An OS normally on real hardware does this to essentially wake up or reschedule certain threads in the OS to do activity or respond to interrupts that come in from hardware. We have to reflect these things back into a guest itself. And then the last notion of time is one that's internal to the hypervisor, scheduling time. It's basically how long has a virtual machine been able to run on a processor. Because we have to share processors amongst guests, every once in a while we'll have to take a processor away from one virtual machine and give it to another. All right, so that said, one of the things that we had to deal with, grapple with, is how do we handle reads from the high-performance timestamp counter, right? This is something in the CPU that ticks by every clock cycle. So if a virtual machine were to do a read from the timestamp counter, do an instruction, and do a read again, well, in real hardware, you'd expect a very small amount of time to elapse in between. In a virtual machine, though, you can actually have a huge jump of time that every once in a while can happen if we take that processor away to give and schedule to another virtual machine, and eventually give it back to him. You can also have a huge jump in time if the instruction that's done in between the reads of the timestamp counter generates an intercept, right? Maybe one of those I/O operations that I mentioned earlier. So, it's kind of coming down to, well, what are we going to do for a guest if it sees the timestamp counter, jumping around in very strange ways? Do we want to stop that? Do we want to make the timestamp counter look like it's always just normally incrementing and not having these big jumps? Because the hardware gives us that ability. You can set in the virtual machine control structure the ability to essentially roll back the timestamp counter, set an offset, so that the guest won't see the time that's elapsed, the processor was taken away from it and given back. So we kind of have, one camp or one way of thinking around, well, we could just allow the timestamp counter to go ahead and jump ahead, right? Let it advance naturally. This can actually happen on real hardware. If, for instance, system management mode were to kick in while an operating system were running. But one of the big problems is that because every once in a while we'll shuffle processors around, we actually might take a physical processor away from a guest and then give a different physical processor back to the guest. And the two processors may have drifted TSCs, right, that very different times elapsed on the timestamp counters. The guest actually has a risk of actually seeing timestamp counter jumping backwards in time. That's not something you'd ever really see on real hardware. So likewise, we have the idea of, well, we can always modify it and make it appear like it's never changed. So essentially, when the processor's taken away from the guest, record where the timestamp counter was, keep track of how long we're operating, and then when we return to the guest, just fix the timestamp counter back up so it doesn't look like it advanced and there wasn't any of that gap time there. And one of the big problems that we look at, though, is that we don't actually exactly know how long it's going to take to return into the guest. Right? There's a single processor instruction that says, when the hypervisor's done, VM run, VM exit, get back into that guest operating system. But based on processor cache, we don't exactly know how many cycles that might take. Sometimes it might take 1,500 cycles. Sometimes it might take 2,000 cycles. There's some variance there. So even if we're trying to fix that up, the guest actually will still see some amount of variance that could still be in some essentially something odd that's going on. So what we realized also is that some software actually needs to know really actually how many processor cycles have actually gone by. An example of this might be something that's keeping track of, for instance, a codec. Like say you have a video codec, taking a stream of video in and transcoding it to another codec. It might actually want to know the fact that it actually just had a big skip in time and it needs to actually throw away or skip some frames or skip some post-processing steps. We have to make sure that still works right running inside of a virtualized environment. So the final conclusion is that, well, we go ahead and allow TSC to go ahead and jump forward, but we'll just guarantee that it never goes backwards in time if we happen to shuffle the processors out. Essentially, the takeaway here is that while there are some things that we could try to do, they're never going to be quite right. And operating system code and applications actually need to know they're being virtualized. They need to know if time actually went away in order to keep processing data and operating correctly. So in the end, we don't mess with it. We just ensure that it doesn't do something completely abhorrent that you'd never see on real hardware, like go backwards. So what are some things to think about when deploying virtualization or deploying Windows Server virtualization, hypervisor? The first one is, how do you patch, how do you update the hypervisor? Well, because the hypervisor under our model is just a device driver inside of that root partition, patching the hypervisor is as simple as easy as doing Windows Update. How do you consider about managing lots of virtual machines? I mentioned before, imagine a data center of 1,000 machines, each running dozens of virtual machines. Well, we provide some interfaces through System Center for managing VMs. I think one of the more important takeaways, certainly for this audience, where we're thinking about securing systems or finding vulnerabilities and weaknesses in systems, is that root partition is very critical. Right? It's a very critical resource on the network. If it's compromised, all the guests that it's running can be compromised. So there's some really, I think, very fundamental best practice recommendations that I can give around this, which is to think about, this root partition doesn't need to run arbitrary applications, right? There's really no reason to run services inside the root partition, right? A web server, database server, things of that sort. The virtual machines are where you want to run those applications. And likewise, the root partition doesn't need to be connected to the internet, right? There's really no need to expose it to that sort of risk. You want to expose your virtual machines and configure them to be exposed to the internet. The root partition, lock it down. Just have it accessed by a back-end network. If you're concerned about updating, right? So there's the technology, Windows WSUS, that lets you have essentially a back-end enterprise update server. That it's the one that goes out and talks to the internet and gets updates, and then all of the systems on a back-end or management network can talk to it to get updates. So that way the root partition really doesn't have any reason to actually have to have communications and hence exposure to risk out to the internet. Another consideration is we utilize no execute hardware NX in the hypervisor. We won't launch if NX isn't enabled. So all the hardware that we support, 64-bit processors with virtualization technologies in them, support NX. Just have to make sure that that's turned on in the BIOS. And likewise, virtualization also has to be turned on in the BIOS in order for Windows Server Virtualization, the hypervisor, to run. And another important consideration to think about when dealing with virtualization, really two virtual machines will really never have the absolute same degree of isolation as two physical machines on a network. Right? While it's the goal to represent that in the virtual environment, and we really do have a strong goal to protect confidentiality and integrity, there is always that risk of essentially that inference, right? Being able to tell that there's somebody else running around there. That could potentially, lend itself to a form of inference attack or utilize covert channels to signal across. So I think, sort of my conclusion or my statement around this with virtualization is I wouldn't recommend running virtual machines of vastly differing trust levels on the same physical piece of hardware. And by this, I'm really talking about the absolute complete extremes, right? A top secret virtual machine and an internet unclassified virtual machine. Or a front-end web server and a back-end certificate crypto server. Last couple slides here, I have some future thoughts on how virtualization is useful or impacts security, right? Things as the security community we can start to think about using virtualization for. And the first part of that is that there are many types of virtualization. Right? I've been talking about hardware virtualization, but there are higher level forms of OS virtualization and software application virtualization. Essentially, I kind of think about it as the deeper you go, the greater the isolation you get, but the greater overhead there is in virtualization. So machine virtualization, strong isolation, lots of overhead. Right? A Java VM or a CLR VM, right? How much isolation, how much overhead? Right? Probably some amount less. I think we're all pretty familiar. Virtualization is pretty useful for doing virus analysis, right? You can put some potentially hostile malicious code inside of a VM, run it, do some analysis, throw it away when you're done. But it's also important, interesting to think about virtualization deployed in an actual live server environment. If you suspect a virtual machine has been compromised, gives you some pretty powerful tools for doing forensics analysis. Right? You could take a snapshot of that virtual machine while it's running and go off and do some analysis offline to look at what the state and what the contents are, right? To look for evidence or trace of malicious activity. Likewise, you could take a series of snapshots over time and sort of see a progression of action that may have happened inside that VM. There are a lot of things that we're thinking about investing in operating system hardening, given that it's running inside a virtualization environment. You don't have any specific things to talk about today, but there's a lot of very interesting, powerful technology here that could be used to actually sort of like those enlightenments of taking faster access for devices, ways that we could actually strengthen or harden the operating system security that's running inside of a virtual machine, things that we could never do with an OS running on a physical box. And the last area is around, virtual machines are most useful, I believe, when you are virtualizing something that would normally be a standalone machine on a network. And so we've talked a lot about servers. There's certainly also the case of having network appliances, say a firewall or intrusion detection system. So what are some ways in which virtualization could be leveraged to actually not just represent physical servers as VMs, but actually network devices as VMs? Virtualization as a technology also brings with it a lot of challenges. Right? Virtual machine to virtual machine network monitoring, right? So normally you have two physical boxes that are talking to each other in a network. You have an opportunity to put an intrusion detection appliance in between them and see the traffic. If two virtual machines are talking to each other over a virtual network, the traffic may actually never leave that server. It might just go across the virtual switch between the two of them. So how do you handle network monitoring in a virtualized environment? I think this is one of the challenges out to the security community to think about ways and the right ways to actually do this. Another big challenge is virtual machine patch levels. When a virtual machine itself, that guest isn't running, right? Say if it doesn't run for a couple months, it's going to get stale. It's going to get out of date. It's not going to get the latest patches on it. So what are ways in which that OS could be serviced and updated, right? So when it's brought back online, it's not exposed to risk and attack. I've already talked a fair bit about that leakage concern, and just simply to say that there really is something here that's a larger attack surface than you really would have on two physical machines, and we have to take that in consideration when we're thinking about securing systems and looking for vulnerabilities. Availability is also always a concern in virtualized environments. I mentioned the sort of flooding attacks. Essentially the notion of having a service level agreement, a guarantee, can certainly be a challenge in a virtualized environment. And then finally, there is the notion of threat of a malicious or an unauthorized hypervisor. I didn't really talk about that much earlier when I sort of had that attack diagram. I was really focusing on a guest getting out. And that's really just because we're talking about, with this, server virtualization. And in a server environment, you're not likely to be running a lot of risky or really any other software at all inside that root partition. And because that's where the hypervisors launch from and that's where it's launched fairly early on, there's a fairly low risk in a server environment of a hypervisor-based rootkit. But by and large, as we want to see virtualization become more widespread, and certainly on client systems, desktops, laptops, this is a definite concern. And that gets now into some of the future security work. A lot of things that we're working with partners and working with the hardware community and Intel and AMD to make happen. One of the big ones is secure launch. Secure launch is kind of an idea of a facility for launching a hypervisor that can have some notion of policy enforced on it. Right? A signature check, right? A hash and a cryptographic signature check to say, well, who actually supplied this hypervisor? Where did it come from? And have the hardware perhaps do some enforcement to prevent an unauthorized hypervisor, right? One that the machine administrator, machine owner has said, here are the hypervisors I want to run. If it's something else, don't let it run. Right? And I really see this as sort of the way that we actually address and can solve in the future the risk, the threat of unauthorized hypervisor-based rootkits. It also provides hardware protection, hardware mechanisms, so that when the hypervisor is launched by that root partition, the root partition can't tamper with the hypervisor during the launch phase, right? That's one of the risks, one of the threats we have today. One of the reasons why the hypervisor has to trust the root partition. That's something that, with future advancements in hardware, we can address. And the other areas, and some of the other kind of hardware and technology coming down the road that has really interesting security implications is DMA remapping. Intel has their BTD technology. AMD is working with something called IOMMUs. They're essentially very similar approaches to solving a problem of, well, what happens in the future if we actually want to give a guest operating system access to a physical device, right? Well, he could do DMA attacks to the hypervisor and the rest of the system. So we have to give the guest gated access, right? Limit the ability for the hardware it's able to use and program from arbitrarily accessing memory. Right? Can we wall it in, gate it in, so that you give a guest a piece of hardware, the guest can only use that hardware, even DMA, into the memory that's been given to itself, and no other partition. And this type of technology can also be used to address that second threat of the root partition against a hypervisor, is to say that, and a hypervisor can also protect itself from even the root partition. Right? So it's the root partition, maybe can do DMA into all partitions except for the hypervisor. So in conclusion, hypervisors is some pretty kick-ass technology, some really exciting stuff here. We're going to have a beta of Windows Server Virtualization available with Server 2008, the release, right? So when it's released, the beta is available. And we're also looking at ways that we can actually get it out maybe earlier to you guys to take a look at. Because, right, we want your feedback. This is pretty still early in the development. You know, we're talking, what, it's 9 to 12 months out here. And so it's not fully baked, right? This is a time in which your thoughts and your input are really valuable to us. So we've got a blog. You can go through and discuss and you know, put comments, ideas, issues there. And then my email address is there. Be happy to discuss things with you in email. Or again, if you see me later in the conference, feel free to grab me and ask me some questions. All right. Thanks. So we have time for a couple questions. Maybe just two or three. Anybody has? Yes. Be sure that.
What's the time frame for putting some of these future work into your stuff? That's one question I have. And any future time frame for putting this kind of technology in client space?
Right. So the questions are on time frames for some of the future technology, some of the hardware technology, and also putting virtualization into clients. I don't have specific time frames I can give you right now. A lot of this is really dependent and driven by what Intel and AMD's time frames are. So essentially, they're the ones that need to answer that question. As for clients, we're looking at how best virtualization can actually benefit somebody in a client environment, right? What are the compelling scenarios? Why would somebody actually want virtualization in a client?
Protect against kernel attacks, like you have the kernel patch protection technology, which is not really not based on 32-bit. So maybe this is a good option for we haven't seen KBB going anywhere. Maybe you can check some thoughts on that. How does this solve that?
Right. Yeah. Absolutely. Absolutely. I think. Yeah, I think that's right on. He's talking about ways in which we could harden the OS, kernel patch protection, things like PatchGuard and like with a hypervisor. Certainly some things that we're thinking about and have some ideas around, but I don't have any concrete announcements or plans on that right now. Okay.
Thank you.
Yeah, do you have a question? Yeah, I think that's a really interesting question around, does the hypervisor allow itself, to have the root partition essentially be interchangeable or replaceable? I think kind of one of the design intentions that we have long term is sort of investing in a small, limited, kind of stripped down hypervisor is to be able to support greater flexibility like that in the future. And in particular, as we start talking about scaling out to large numbers of cores and virtual machines, some of these things become a little bit more interesting. Great. Thanks. We're out of time, but if you want to see me afterwards, be happy to talk to you.